Welcome to the continuation of an aero design video from Ultralight Airplane Workshop. In this video, we're going to continue coming up with the initial weight estimation and the CG for the UWS-4 Ultralight airplane. Now this is part B of the video. In part A of the video, and I'll put a link up into the upper right hand corner to part A. In part A of the video, we looked at the equations that we're going to use for coming up with the initial weight estimation. Now the equations we're using, we got from Dan Raymer's book, Simplified Aircraft Design for Homebuilders. And I believe Dan got that from a document from Rockwell, the Aero Commander group, came up with a set of equations for estimating the wing weight, the tail weight, vertical and horizontal, and fuselage weight of an aluminum airplane. So in part A, we went over that, looked at how the equations put together, looked at how to use them, and then came up with some reasons why they probably aren't directly applicable to an ultralight airplane. Close, but not quite. Well, here in part B, we're going to go over some corrections to these equations so that they are hopefully give us a better weight estimation for an ultralight airplane made out of aluminum. So at the end of part B here, we're going to come up with the initial weight for the UWS-4 Ultralight airplane. Now in part C, we're going to figure out the center of gravity for the UWS-4. So now we're going to pick up right where we left off in part A and continue with looking at these equations and what we might do to change them a little bit. Instead of jumping right into where we left off in the old video, I think maybe just a very, very fast overview of what we talked about in the last videos is probably warranted. So stick with me for just a minute here. So for example, this is the wing equation that we looked at in the old video. So basically it is a bunch of different parts. So there's a constant up the front, and then there's a bunch of different parameters for the wing. And this would also apply for the horizontal tail surface and the vertical tail surface. And then these various parameters are raised to some power, this exponent. And so for example, the planform surface area aspect ratio, in other words, the ratio of the span of the chord, the sweep of the wing in degrees, the ultimate load factor, which is going to be your regular load factor, like 3.8 Gs, and then you multiply that by 1.5 to get your ultimate load factor. The design gross takeoff weight, the thickness over chord ratio, the dynamic pressure, and the wing taper ratio. That would be the chord at the tip divided by the chord at the root. And so what we're going to look at now is these exponents and this constant for the wing and the horizontal tail and vertical tail, and see what we can learn about these exponents. Because we don't think these equations may be directly applicable to ultralights, they'll probably be off. But by trying to understand these exponents, maybe we can figure out how to fix them to work for ultralights. So now let's get going. Okay. Now here's something that I found interesting, which is comparing the exponents for the wing, vertical tail, and horizontal tail. So for example, on the surface area of these, looking at these components here, wing, horizontal tail, and vertical tail. Just looking at the size of these, it's interesting that for the horizontal tail, the surface area has a bigger impact on the weight than it does for the wing or the vertical tail. Although surface area for the vertical tail has more impact than for the wing. So I thought that was kind of interesting. So basically that means the skin is a fairly significant part of the weight for the horizontal tail and vertical tail, not quite as much for the wing. And then for the aspect ratio, I was a little bit confused by these values here, because you look at the size of this exponent for the wing and for the horizontal tail. Now I would have expected them to be similar, but for some reason the aspect ratio has almost no impact on the horizontal tail, which it has a fairly significant impact on the wing. That kind of surprised me. I went back and double checked these numbers, and it seems to be right, so I guess it is what it is. For the design weight of the airplane and the load that it can carry, there's not a whole lot of difference here how that impacts the wing, horizontal tail, and vertical tail. It's roughly the same. Vertical tail doesn't seem to be quite as much impacted by the load that the airplane can carry. But the wing, since it's carrying most of the load, of course, it gets impacted the most. Again, let's look at dynamic pressure. So for the wing, the dynamic pressure, the speed of the airplane basically, has very little impact on the design of the wing. And I have a feeling that's because it's going to carry so much weight and has to be built so strong to carry that weight that you're already taking into account the dynamic pressure, basically. But it's not quite as true on the horizontal and vertical tails, so speed does have more of an impact on them. Not huge, but it does have more. And then taper ratio. Now this is another odd thing that I haven't quite figured out. So the taper ratio of the wing does have some impact. It's not huge, but there is some impact on it. But notice this, on the horizontal tail, it's actually negative. So the taper ratio has the opposite effect on the weight of the horizontal tail compared to the wing, which is very strange. The more rectangular that horizontal tail would be, the lighter it would be. Whereas it's the opposite on the wing. The more rectangular it is, the heavier it'll be. But the vertical tail is like the wing. So the more rectangular you make it, heavier it'll be. And then when you come down to thickness, it's pretty much the same on all of them. Thickness has a pretty big impact on the tail. The thicker you make it, the lighter it'll be. On the wing, the thicker you make it, the lighter it'll be. It's, you know, in the rough same area, 0.3 to 0.49. But for the horizontal tail, it has less impact. And again, I don't know why that is, but the equations seem to work. So I got to thinking that the Raymer equations, I shouldn't call them the Raymer equations, they came from Aero Commander, but the equations in Dan's book will probably not be directly applicable to ultralights. They're probably going to be giving some slightly off answers. Now I should specify that would be for aluminum airplanes. And the reason I say that is for an aluminum ultralight, we've got a minimum gauge problem. So for our wings and our vertical tail, horizontal tail, the fuselage, in this case on the UWS-4 booms, they're going to be aluminum sheet. And the minimum gauge you can get on aluminum sheet, I shouldn't say it's absolute minimum, but typically that's 16 thousandths of an inch. I've heard you can get 12 thousandths, but it's like dealing with aluminum foil. It just bends and warps too easily. So let's just say the minimum gauge for ultralights would be 16 thousandths of an inch. No matter how thin we would like to make these skins on the airplane, we can't go below 16 thousandths. Well, when you start looking at a lot of the lightweight general aviation airplanes, there are a lot of places on their wings, on their tails, where they use 16 thousandths. But they're using 16 thousandths or maybe 20 thousandths because of the loads. The thickness of the sheet matches the load that they need to have the sheet carry. For us, what will happen is 16 thousandths is far, far more strong than we need to carry the load, which means we're carrying around extra material, extra weight on the plane. So that's why I was thinking that the Raymer equations may not work for ultralights. Another thing that I think that will be a significant factor is the amount of payload relative to the empty weight of the airplane. So, for example, the Cessna 150, the maximum useful payload on that is less than a third of the total gross takeoff weight of the airplane, if I remember the numbers correctly. But for us on our ultralights, depending on how you design it, our useful load can actually be more than half of the gross takeoff weight. So that's a big difference, going from less than a third to more than a half. And so that will also probably have an impact on the equations from Dan's book. Now, I haven't done detailed design on the UWS-4 yet, which is why we're using these equations. But I'd like to use them, but using these equations I think will probably give me a wrong value. So in order to figure out how close they will probably come, I decided to use the Ultra Cruiser as an example, the Hummel Ultra Cruiser. Now I have plans for the Ultra Cruiser. It's a 2002 version of the plans. Now I did something that's taking me forever to do. I've spent most of the month doing it, doing a little bit here and there because it's very tedious. But I made a spreadsheet of adding up the weights of the various parts of the Ultra Cruiser to get a baseline, and then I would use the Raymer equations and compare the two. So I made a spreadsheet to do that. Let me bring that up real quick. All right, so here's the equation data. I'm not going to go into all the detail of the equation. I'm just going to give you an idea of what I did, and then we'll look at the comparisons. So just real quick, for example, I did the wing, and I went through the plans and looked at every single part of the wing. For example, forward skin, top skin, bottom skin, aileron skid, aileron ribs. There's more than one aileron rib. There's wingtip ribs. for the trailing edge, aileron hinges, the spar caps. And by the way, all that part is for the outer panel, because there's a center panel and 2 outer panels on the wing. So I did all of this for the outer panel. I also took into account the rivet holes. Now, after a while, I figured out, at least on the skins, it's not worth doing it. Rivet holes don't change the weight enough, so I quit counting up rivet holes. But at least on this outer panel, I did it. But I did count up rivets, and so that gets included down here in hardware. So a number of rivets, different types of rivets, like solid rivets, steel mandrel rivets, aluminum mandrel rivets, the AN3 6 nuts and bolts, AN3 11 nuts and bolts. So I added those up. So for example, the outer panel, I came up with 57 pounds, excluding the hardware. And then I did the same thing for the central panel. Oh, by the way, that was 2 panels. I multiplied by 2. And then I did something very similar for the center panel. And then I added up the hardware and the center panel, and I got 88 pounds. So I did the same thing for the horizontal tail, vertical tail, and I did the fuselage too. And by the way, I did the same thing for the landing gear, because I will probably use very similar landing gear on the UWS-4. So I calculated up what the weight of the landing gear is. So now we can come back here and talk about something I said I was going to talk about later. So here's the Ultra Cruiser. Now this is using Raymer's values. So Raymer's values came up with 69 pounds. Now we were just looking at, let me go back up here. So 69 and 88, basically 89. So about a 20-pound difference. So that's quite a bit for ultralights. 20 pounds is a heck of a lot of weight. So it is off, and it is less, which I expected because of the minimum gauge issue with aluminum. So I wanted to come up with a way to change these exponents, or the constant up here at the front, to come up with a better value. Now, I think the minimum gauge is probably the biggest component of the weight of the wing. So I decided to change the exponent for the surface area of the wing, and that's why I did pink. So here's the original equation, and I changed the exponent until I got 90 pounds. 89 is what we came up with. We calculated parts, so 90 pounds. I changed from 0.738 to 0.795. And then I took this exponent, the new one that I came up with, that makes the numbers match what I think is reality, and I used that over here on the Ultra Cruiser. So when I did that exponent calculation, I came up with 85 pounds. So it says it's 5 pounds less than the Ultra Cruiser. Now I was expecting the wing for the UWS-4 to be a little bit heavier than Ultra Cruiser, or 5 pounds lighter. So I'm going back and looking at some things, trying to figure out why that is. I recalculated my thickness for the Ultra Cruiser wing and found out I made a little bit of a mistake. Now I used a little equation to do the calculation here. This right here should have been 47. So we're at 69 now. That changes it to 69.6. So that really doesn't make a difference. So that's not an issue. So let me just undo that for the moment. Now if we come up here and look at the aspect ratio. Aspect ratio for the UWS-4 is 4.4. I wanted to be 4.5 originally, but this is close enough for now. But for the Ultra Cruiser, it's roughly 5. So let's come down here and look at our modifier difference. So that goes from 2.43 to 2.77. Well, let's see what would happen to the Ultra Cruiser wing if we had the same aspect ratio. So let's put in 4.4 here. So that drops it down to 78. Okay, so increasing the aspect ratio really increased the weight of the Ultra Cruiser wing according to this calculation. So we're going to go ahead and stick with what we have here, 85 pounds for the UWS-4 airplane wing. So I did basically the same thing also for the horizontal tail and the vertical tail. So I came up with a change in the surface exponent once again. I went from 0.896 to 1.09. Again, using the Ultra Cruiser values to do that. So we underestimated, I think, the Ultra Cruiser horizontal tail's weight. I calculated it should be about 8.7 pounds. The equation came out with 5.3, so that's how I came up with this change in this number here. I just kept changing it until I got what was right. Now, when I used this for my horizontal tail, I came out with 14 pounds. I think that's going to be too heavy though. And the reason it's so heavy is the surface area. So the initial estimated really rough guess using volume method to determine the surface area for the horizontal tail came up with 21 pounds for the UWS-4. For the Ultracruiser, it only has a 12-foot square area. So that's a big difference. That's mostly why it's so heavy. Now, I think when I get done doing a more detailed calculation for the surface area, after I figured out the position for the forward and aft center of gravity, I can probably make this surface area smaller. But I'm going to leave it up here for now. And basically did the same thing for the vertical tail. So once again, made a slight change. It's very similar to the horizontal tail from 0.873 to 1.05, using the same thing. Coming up with the equation using Raymer's for the Ultracruiser, calculating what I think that weight is, summing up all the parts, then using that same exponent over here for the UWS-4, and then coming up with 5.5 pounds. And again, I used the volume method to do it, and that would give me a heavier or a bigger surface area than it would for the Ultracruiser. Eventually, I can probably reduce that down, but we're going to go ahead and go with what we got here. I did the same thing down here for the fuselage weight, but it won't really apply to the first version of the UWS-4 because I'm doing something completely different. I'm basically having a beam instead of an enclosed fuselage. So I did the estimation, but then I'm not going to be using it. Oh, by the way, I did not verify that I had the equation correct using the Cessna 150 like I did on all the other parts. So there's very possible that there's a mistake here, but I kind of doubt it. So I made this slide here kind of summarizing the changes I made to exponents. For the wing, horizontal tail, vertical tail, I just changed the surface exponent, and here's what the old value was and what the new value is. And again, for the fuselage, what I came up with there. So that's in the future, if I lose my spreadsheet, which is certainly possible, I could accidentally delete it when I'm cleaning stuff up on my files, then I should be able to come back and find this video and find these values. Now, since I just used plans and measurements off the plans in order to try to calculate weights of the parts for the Ultracruiser, wing, and horizontal tail and vertical tail, I could have easily made mistakes. I could have left some stuff out. So I have a request for you guys. If any of you have built an Ultracruiser and you weighed, let's say, the outer panels, the center section of the wing, the elevator, horizontal stab, the rudder, the vertical stab, if you weighed any of those, I would love to know what you got for those measurements. And would you leave a message on the comments in the video and let me know what weights you got. Now, I'd like to have more than just the Ultracruiser to base some of these changes on the exponents. So, if you have built an all-aluminum ultralight airplane other than the Ultracruiser, I'd love to know what your weights were too, including the fuselage weight. I should have mentioned that for the Ultracruiser. So, something like the CA2, or maybe you have something like a Merlin Light and you've taken some of it apart, taken the wings off, taken the tail off, and if you weighed that, I'd love to have those measurements too. Now, I'd like to have some of this information for more than just aluminum airplanes too. So, if you have measurements, weight measurements that you've taken for a wooden fabric airplane, I'd love to have those measurements. Let's say a tube and fabric airplane, like the Ultra Pup. I'd love to have those measurements. Now, I do have a Quicksilver MX with ailerons, so I can measure those, and I also have a weed hopper, so I can measure those too. But any other planes, like say a Kolb, Challenger, any of those, I'd love to have some of those weight measurements. So if you can do that, thank you very much. Now, like I said, the goal of this video is to come up with an empty weight estimation for the UWS-4 Ultralight. So now we have some of that. We have an estimation for the wing, an estimation for the horizontal tail, and an estimation for the vertical tail. But there's more to it. There's a lot more to it. Like the beams, I don't have a good way, at least using Raymer's equations, to come up with the weight for the booms, because we have a twin boom design. And there's all kinds of other things that we need to take into account, like the landing gear. Now, some of these things I can come up with some decent values. You can actually look online, for example, for ultralight tires. So I actually found some tires and I put an actual number here for them, and for the tube, and for the wheel hub. You can go look that value up. Now, as I mentioned before, I took the Ultracruiser leg. I figured out, so I did basically the same method like I did for the wing and horizontal tail and vertical tail. Calculated a leg weight, so that's per leg. And then I add all these up, multiply by 2, and that gives me a main landing gear weight of almost 10 pounds. I think that's probably underestimating it. By the way, I did not include brakes, which I intend to add. Now, this landing gear isn't really a whole lot of weight, and it's fairly close to the CG, so being off on that doesn't really bother me. As long as I'm not way, way off, like 100 pounds, which of course it shouldn't be. Nose gear weight, I just took one of the main gears and called that the nose gear weight. Now that one does have more of an impact as it's farther out front, farther away from the CG. So I probably should give that a little more consideration, and in the future I will. Especially as I start getting into the detailed design. I don't have a tail wheel, so I put 0 in for that. That's why it's red. Propulsion, I actually got real numbers. So for the Herth F-33, 28 pounds for the bare engine. And then for an engine mount, I'll talk about how I calculated that here in a minute. The exhaust, 7 pounds. Redrive, 5 pounds. I found these values online. For an Ultraprop 2 tube blade is 6 pounds. So I add all of that up. So for the propulsion area, that's 50 pounds. That's really not too bad compared to like a half VW, which is up around, what, 90 pounds, something like that, 85 pounds. And then I took a guess on the seat at 3 pounds. It's probably not too far off. I need to come up with the value for the seat belt. I haven't done that yet. Fuel tank, I just took a guess on that being 3 pounds. Instruments, it's probably overestimating it, but that's okay. Electrical's overestimating it, and I just took a fairly wild guess on flight controls. But flight controls are, let's see, that's a little bit behind the CG overall, a little bit of it in front of it. So being off on that probably isn't too important. So I add all this stuff up, and I came up with 223 pounds. So I'm about, what, 27 pounds less than the current limit that we're allowed in the US on Part 103, which is 254. But clearly this is, I think, too small a number. I think I'm going to be up really close to 254 pounds. So some values here are underestimated. For example, I'm pretty sure the wing is underestimated. I'm not worried about that though, at least not yet, because the wing is very close to the center of gravity. So being off on that isn't going to hurt me. That's perfectly fine. Having the tail be off, that could actually hurt me, being too heavy or too light. Right now the values are pretty heavy, so that's overestimating them, so that's probably okay. It kind of depends. But I do at least have an initial number that's not completely out of whack, but it's off by about, what, 10%, something like that. But it does give me hope that I can probably maybe get in under that 254 pound limit. Now let me talk about how I came up with an estimation for the boom weight, because I do have an estimation here and it's not a complete wild guess. Here I've brought up the program OpenVSP, and I'm using OpenVSP version 3.35.2. Now the reason I want to use OpenVSP here is that it can do an estimation of weight and it will calculate center of gravity. So what I've done is I've gone into the wing. Let me bring that up. So here are the wing parameters. I went into the mass area and playing with density, and I turned on include thin shell with this little yellow button here. I've played with these numbers to get it to come up with the correct weight value. So we want 85 pounds. That's what we came up with using the Raymer equation with the modified exponents. So let me show you how I went about that. So let me get rid of everything else here. I'm going to do a show only. So now I only have that wing. I'm going to come up to the analysis. I'm going to come down to mass properties. That brings up this. I'm going to calculate mass on what's shown. Right now it's just the wing. I want it to draw the CG also. Now right now it doesn't truly matter, but later on it will, so I'm going to keep it on. What the program will do is it'll slice along here. Now I'm having it slice in the X direction, so it'd be nose to tail will be the slices. It'll slice along here, figuring out what the surface area is and the volume is, and it'll do estimations on that little area midway between one slice and the next slice, and then it adds up all the slices. Now I'm doing 200. Roughly the maximum it can do is 200. 199 is going to take too long. Let's go down to 75. I've got the wing showing here. the set we're going to do the computation is what's shown. So let's do the compute. So what it has done is, let's bring this down here, it has made a mesh geometry and then slicing on that mesh geometry. So you can see it came up with 86 pounds and we wanted, what, 85 pounds. So that's good enough. So now what I can use is I can use those mesh properties we were just looking at. Let's bring that up again. Let's do these mesh properties, show only. We do mesh properties, 0.22 for skin and 0.44 for the volume. And we can calculate the boom weight. So let's go ahead and do that. So let's bring up the boom. Let's do a show only. Let's go ahead and stick with 75 here. We can take a look at it a little bit better. So there you can see the boom. So let's compute that. So again, we're only going to compute what's shown. Compute. So we came up with 17.4 pounds roughly. And I had 17 pounds in the spreadsheet. So that works out pretty good. So this is another really rough way to do component calculations. And what's really nice about this is it calculates the position of the center of gravity. So in the X position, the Y position, and the Z position. And that's this little red dot right here. So I have a value for the empty weight of the airplane. And for the moment, it's good enough. I can use these values to at least get an initial center of gravity, which is what we're going to do in the next video. So once we get that initial center of gravity, we can start working on some stability analysis, which will actually make us change the size of the horizontal tail, I imagine. It'll probably get smaller. And then not soon after that, we can start working on some detailed design. We'll design the center section. We'll actually probably get really detailed and actually build a center section. And I can actually also build the booms, the landing gear, at least the mains on the landing gear, the horizontal tail, and the vertical tail. Because those are going to be, I believe, unchanging. I think they're just going to stay the same no matter what. What can change, though, is the fuselage or the boom and where I place the pilot and the nose gear. And then I will move those to get the center of gravity that I want. And then I can finish the detailed design on the pod or the boom, whichever I go with. And I think I'll go with a boom to start with instead of a pod for the fuselage. So I'm pretty excited. We're getting closer. So in the next video, part C, we will use OpenVSP to get our initial center of gravity. Well, guys, thanks for watching. Until just a few days on part C.